Howdy everyone, Dr. Niregev here, and before we dive into the topic of CFAR detection in radar, what I want to do is at least get you familiar with the concept of hypothesis testing in statistics, or the start, just the tip of detection theory and likelihood ratio tests. All right, so let's get started. Let's do the likelihood ratio test. Also called LRT. All right, and we will start by defining a problem. Let's say that we're sampling one sample. Okay, it's not a vector of samples, it's one sample just for the sake of simplicity. And let's say that we have two options. One hypothesis is what we also call the null hypothesis, is that our sample is just noise. And the noise sample is distributed Gaussian with zero mean and sigma squared variance. And the alternative hypothesis, H sub 1, is that we are sampling the signal S, which is a scalar value, plus the noise, same noise. Okay, and now we are getting a sample. We're sampling X, and we have to decide, is X representing a signal, or is X representing no signal or only noise? Okay, in other words, what we have down here is a PDF value. This PDF represents the PDF of X under the null hypothesis, under H naught, and we will call this Gaussian. This Gaussian will be F of X under H naught, and this Gaussian, which is shifted by what amount? By the amount S, okay? And we will call it the PDF of X under the alternative hypothesis H1. Okay, now the most, I would say, trivial thing that we can do, or the most straightforward and even intuitive thing that we can do, is just put a threshold here. Let's call it gamma. And everything above gamma, we say it's the alternative hypothesis, or it's the signal. Anything that we get below gamma is only noise. Okay? And we have to set this gamma in a way such that we want the false alarms to be as minimal as possible, and we want the detection probability to be as maximal as possible. Okay? Now there is a give or take here. It's just a blanket, and it's a fixed length blanket, and we have to decide which part of the body we want covered, the toes or our face, so to speak. Okay, and we will see that the false alarm and the detection, they move up together and move down together. So we can't run out from that. That's a physical phenomenon. And let's see it here. Okay, so what is the false alarm? The false alarm is this area, this pink area here. Okay, the area under this curve, the PDF of X under hypothesis H naught. Okay, and if we write it, we can write that PFA equals the integral, the area, from gamma to infinity of what? Of the PDF of X under the null hypothesis. We're integrating over X. Okay, this is the X axis. Similarly, what will be the detection probability? The detection probability will be all this blue area. Okay, in other words, it's the P sub D, the detection probability, is the integral from gamma to infinity. The limits are the same, but now we're integrating over the other PDF, which is f of x under the hypothesis H1. Obviously, we're integrating over dx as well. Okay, so if we have a noise samples can also be generated from this tail with low probability, hopefully, but it can happen. So this tail represents all the false alarms, all the noise samples that we will decide that they are signals falsely. Okay, and similarly, from gamma, the integral from gamma to infinity over this Gaussian, the Gaussian that represents the signal plus noise, will be the detection probability. Okay, 1 minus the detection probability is the miss probability, which is the tail area under this PDF. Okay, now what we want to do is we want to maximize the detection probability while keeping the false alarm constant. That is the concept of constant false alarm rate detector. Okay, let's write it down. So we will use Lagrange multipliers. Lagrange multipliers. The Lagrangian will be L of x, which is, we're maximizing PD, under the constraint that our PFA is some constant. Let's call it alpha. Okay, by the way, in statistics, the PFA is actually denoted by alpha, and it's type of error number 1. They call it in statistics. Okay, and we have now to maximize this with respect to x. Let's write what this is actually in terms of x. So that's the integral from gamma to infinity over what? Fx under hypothesis h1 dx. And now we have plus lambda. And now we can start a bracket here, and we can put the integral for PFA. The integral is the integral from gamma to infinity over the null hypothesis PDF dx minus alpha. Okay, and let's write down what it gives us. It gives us, let's take the integral from gamma to infinity out, and here inside we will have f of x under h1 plus lambda f of x under h naught. Okay, all of this with respect to x, and we will also have a constant term here minus lambda alpha. Okay, now in order to maximize this with respect to x, we need to take all of the x's that contribute a positive value to this integral. In other words, the integrand, this term here inside the integral, we will choose x's such that this is positive. So we sum only positive value. We don't want to take out from the sum. We want to maximize it. Okay, so we write that f of x under h1 plus lambda f x under h naught is greater than 0, and that will give us, let's divide by f of x under h naught, both sides. Obviously the PDF is a positive or non-negative value. Okay, let's assume it's positive, so we can divide by it. And we're taking all of the x's that are positive anyway. We're not taking x's that are 0 or negative. Okay, so we get that f of x under h1 over f of x under h0 is greater than minus lambda. We can call this guy gamma, and now we have a test. When x is coming in, we put it inside the PDF under h1, we divide it by the value of the PDF under h0, at an H naught, and we compare it to a threshold, gamma. Okay? And that's our test. That's called the likelihood ratio test. Why? Because it's a ratio of likelihoods. Okay? By the way, this test is a random variable. It's a scalar. It's a random variable. And this random variable, it has a distribution under both hypotheses. Can be different distributions. And we can ask ourselves about these random variable questions. Okay, but this is for another lecture. Okay, so this is the likelihood ratio test. Okay, how do we choose gamma? That's the Neyman-Pearson theorem. Okay, we know that the integral from gamma to infinity over what? Over f of x under h naught dx equals alpha, a number that we choose. For example, 10 to the minus 5. Okay? And now we are solving this equation with respect to this threshold gamma. So gamma will be a function of this PFA alpha. Okay? This false alarm rate. And this is how we choose gamma. This is the Neyman-Pearson theorem, and it's called Neyman-Pearson. Okay? And we are choosing gamma such that this integral is a constant PFA that we chose. All right? So that's the way it works. Obviously, we can see from this picture, from this image, if we take gamma to the right, we get less false alarm, but we also get less detection probability because the areas are smaller. If we take gamma to the left, we get more false alarm because the area now under the left Gaussian will be bigger, but also the area under the right Gaussian will be bigger. Okay, so by taking gamma down, we increase both PFA and PD. By taking the threshold up, we decrease both of them together. Okay, so this non-monotonously decreasing function, PD and PFA are changing together in this. So we can't increase PD and take PFA down, but we can definitely fix PFA, choose gamma such that PFA is fixed, and then we are maximizing the PD with this PFA, like we did here with the Lagrange multiplier. The test that is maximizing the PD under the constraint of a constant false alarm is called the likelihood ratio test. Okay, and this is the first piece of mathematics and theory we need to understand before we go ahead and we derive the well-known radar CFAR detection or detector. Okay, so I'm going to stop here. This is the first part of lesson 1, or I think it's lesson 2 of the module CFAR detection, and I'll see you next lesson. Thank you. Bye-bye.